Hey there, awesome physics students. Let's talk about stress-strain curves, or in other words, how do we get most materials to behave like a spring? First of all, let's think about a particular situation where we have a wire and we're pulling on each end. We're trying to stretch that wire by a certain amount. So let me just draw this up here. So we have a really thick wire that we're pulling on each end with some force. And we want it to stretch. It has a length L, and we want it to stretch a certain amount, delta L. Of course, compared to a spring, it's going to be very difficult to get this wire to increase a noticeable amount. But it will behave like a spring. And now if it does behave like a spring, the spring constant is going to be enormous. That is, it's going to take a huge force to stretch it a noticeable amount. But it will behave like a spring. And if you recall, the spring force versus elongation curve looks like this. So the more I pull on it, the more the spring will stretch, or the more the wire will stretch. And we get a linear relationship like this for springs. Now, the slope of this is the spring constant K, so for a real material like copper wire, that's going to have an extremely steep slope, but it will behave like a spring. What I want to do here is change this graph, alter it, so that this graph will be identical for all things of a certain material. So imagine this is a copper wire. I want to change this graph so that copper will have one graph independent of the size and shape. I want to compensate for the size and shape effects. So let's think about one of those effects. One of those effects is the thickness. I think you can intuitively understand that the thicker wire is going to be more difficult to stretch than thinner wire. So let's imagine stretching a thin wire we'll pull on that with the same force, and that wire is going to have length L here. We're going to keep that constant. And that's going to stretch a certain amount, delta L. Now, how can I understand how does the thickness come into play here? Well, imagine if I have this thin wire, if I just added another thin wire that's identical to it and I stretched it, I would have to put the same force on it to stretch it an amount, delta L. Now, what's happened here is that to stretch the pair together, if I treat them as one object, I have to exert 2F to stretch it the same amount, delta L. What has doubled about these? Well, the thickness has doubled. And by thickness, I mean if you were to take the wire and cut it and look at the face that you cut, that's the cross-sectional area. That has doubled. We get one area here and one area here. And so there's two of those, and so there's two areas. And so what I'm going to do is if I divide the force by the area, that is, if I double the force, that means but I still get double the area, this whole thing will be constant. And so what I want to do over here is divide this force on the vertical axis by the cross-section area. So a bigger, thicker wire will have a bigger area, but it will also require a bigger force. A thinner wire, smaller area, will require a smaller force, and then those two will be directly comparable. Okay, so that compensates for the thickness of the wire. How do I compensate for the length? So imagine that I have a wire of a certain thickness now, and it has a certain length, and I put a force on that to stretch it, and that one stretches an amount, delta L. Let me change the length of this wire. I'll take an identical section of wire and attach that to the very end of this wire here. And of course, because these are end to end here, if I put a force on the end, the tension in both of these will be the same because the tension is the same throughout the rope. This isn't a rope, but it's a wire. The tension will be the same in both of these. This one will feel a certain tension, and it stretches by delta L. This feels the same tension. It's also going to stretch by delta L. And so the total stretch of this will be 2 delta L. It will, this just says that longer wires will stretch more than shorter wires, right? So how can I correct this for the fact that the wire is longer? Well, there's two lengths of the wire L, and so the total length of this whole wire is 2L. So I just divide it by the total length. And so this will compensate for the fact that a longer wire will stretch a larger amount. Okay, so let me just divide this by the total length. And again, a shorter wire will stretch less, but you're dividing by a smaller number here, so the whole thing will be bigger. A bigger wire will stretch more, so delta L will be bigger, but then L on the bottom will be bigger, and that will be the same for the short wire or the long wire. So this is what's called a stress strain curve, and this quantity up here is the force per unit area. That's called the stress. And we often use the Greek letter sigma for that one. It's going to have units of newtons per area, has units of meters squared, so it's newtons per meter squared. It's the same units as pressure. This is called the strain, and it has units of, well, let's see, units on top are stretch, that's in meters, and the bottom has units of meters, and so this has no units. Okay, you can think of this strain as the percent increase of the wire taking, or the object, taking into account that longer things will stretch more. And stress, you can think of it like the force per unit area, taking into account that thicker things will require more force to stretch the same amount. Overall, if you construct a graph like this, then copper will have one particular shape and slope. If you use a different material like iron, it will have a different slope, but the key is that that graph will be the same for all pieces of iron because you've compensated for the size and shape of the particular piece of iron that you're talking about. All right?